he's received many awards, including the LICS, the Logic and Computer Science Conference Test of Time Award, the Computer Aided Verification Conference Award, and various other awards, and he's for some very fundamental contributions to verification of time systems and in general program verification. So this.
Thank you, Martin, and thank you for giving this opportunity to be here. It's great to be here. And I'm going to tell you about a very theoretical topic, but hopefully I'll try to convince you that it's relevant to the title of this workshop, which is about software reliability. So we use regular languages in many contexts, and it's basic deterministic finite automata. It's a very natural model, very intuitive model. And this is one area where the theory has been very successful in practice. The basic theory is very elegant, and regular languages have multiple characterizations and very nice algorithms, for example, for minimization, for learning. And the basic theory was developed in 60s, and now we take it for granted, and we see applications of regular expressions, automata everywhere. In fact, this morning in Professor Basin's talk, he was using lots of automata constructions and formalization using language theoretic concepts. So the question I'm interested in is what's the analog of regularity for defining functions? So here by function, I mean functions that map strings to strings. Now, before we get into this theory, your first question would be, do we really need this? Or is it like what's motivating this problem? And let me give you a few examples. So in fact, I got interested in this when I saw this wonderful project by Sumit Gulwani at Microsoft Research. So this is a tool called FlashFill. And what it does is it learns the Excel macros by example. So let's suppose you search for PL researchers named Martin, and you get a bunch of names, and you get that data into your Excel spreadsheet, and now you want to clean it up, and you want to write each name in some uniform format. So to do this transformation, you have to write, there is no automatic button within Excel that will do this transformation, so you have to write a program. But it's a very simple program. It's transforming strings to strings. And the idea here that Gulwani had was let the user give a few examples, and then his tool would search through the space of all programs and try to find the best program that matches all the inputs. Now, as someone interested in language theory, when I first looked at this, I said, oh, but isn't there like a nice learning algorithm? So in particular, if I told you about the problem of learning automata or a regular language from examples, there is this very nice algorithm called L-star algorithm developed by Angloin. And so that's what I would use for implementing this. But the algorithm that's within FlashFill is a very ad hoc algorithm. And in fact, there is no good algorithm for learning string transformations. Here is another example. So a lot of you actually must be working on verification of heap manipulating programs. So in particular, here is some program for manipulating lists. So a list is represented by, you have a sequence of linked cells with next pointers and so on. Now, we don't really need to know what this program is doing, but if you think abstractly, what such a program is implementing, it's a transformation from a sequence of data items to a sequence of data items. And many of these are actually simple transformations, like insert, delete, reverse, and so on. Now, in the world of protocols, we many times model things using finite state automata and use automata constructions. And there's nice theory also and practical tools for verification of finite state systems. So what would be the analog of verifying sort of finite state list manipulating programs? And in fact, nothing exists. And there is actually an old result by Ramalingam which says that even for very simple programs, if you want to check whether two pointer variables point to the same cell at any point, that problem is undecidable. So in fact, if you look through the literature, everything is undecidability result. And of course, people have developed a whole variety of heuristics, but there is no sort of class of algorithmically verifiable list processing programs. And my third example is document transformation. So here, so I want to transform documents. So here is some BibTeX looking file. And so maybe while writing this file, I made some mistake. And now I realized, oh, actually, these titles should be shifted one entry up, right? So maybe the entries are a bit jumbled up. And so these three fields, author, title, conference, appear in different orders in different entries. And the first entry is missing the title, and actually that's in the second entry. And the title of the second entry is in the third entry. So this is actually a practical problem. I mean, you may want to take a document and then write a transformation for that. So I don't know if you are given this task, how you would solve it. But I think a popular choice would be something like set. So this is a special purpose language for transforming documents. But SED is actually a Turing complete language. And to implement this particular transformation, you would really have to write a loop. I mean, in SED, you can write loops. And there are some predefined macros for deleting some symbols or substituting a particular phrase by some other phrase. But if you want to do something slightly more complex like this, you would really have to write a program with loops, and then no analysis is available. In fact, it's easy to write a program in SED, which will take forever. So the general problems that we see with general purpose programming languages show up there, right? And so the question is this transformation an easy transformation or not? And is it, can there be a robust theory for this? So hopefully by the end of this talk, I'll convince you that there is a very nice fundamental class that's waiting to be discovered and has lots of nice properties. And so what I really want to study is go from regular languages to functions. But just going back to the basics of complexity theory, so when you start the course on theory of computation, in the first lecture, the instructor tells you that well, we are really interested in solving problems, but in theory of computation, we are going to view everything as a language. We are going to convert it into a decision problem, and the answer would be yes or no. So the problem will be encoded by a string, and then it will be, the yes instances would be a subset of all strings, and the structure of such languages is what we want to study. And then we have this classification. We have recursive languages, NP languages, P languages, maybe things that are computable in linear time, and then regular languages, right? So what happens if we go to functions, right? So instead of sets of strings, strings to strings. So the first thing is for things like recursive NP and P, the choice does not matter. In fact, it's very easy. It's very so trivial to take a function, encode it as a language, and in fact, the notion of what's recursive doesn't change at all, right? In fact, the machine model is the same. Everything is the same. And the same holds for NP, P, linear time, but not for regular. So the natural starting point for regular functions would be, let's just do a variation of classical finite state automata. Well, that won't be too exciting, but let's see what happens. And people studied this, in fact, in the 60s. And so this model, the first model for string transformations, is called finite state sequential transducer. So I'm assuming everyone knows DFAs. So you take a DFA, and now instead of labeling transitions with input symbols, you label them with an input symbol and output string. So a typical transition may look like if the machine is in state Q, and if it's reading the letter A, it outputs the string 0, 1, 0 and goes to state Q prime. So with this, you can implement things like delete all A symbols, or replace some substring by some other string, or duplicate every symbol. So it's not theoretically that interesting because it's essentially a variation of DFAs, but has found some applications in speech processing, language processing, but it's not expressive enough. In fact, in all the examples that I showed you, none of them could be modeled like this. If I want to swap first name and last name, this cannot do it. If I want to reverse a list, that's the first programming assignment that we do in list processing program, it cannot be done. And that BibTeX file transformation that I showed, shifting entries up, it cannot do it. So how about two-way transducers, right? So again, in automata theory class, we see for acceptors, one-way acceptors are same as two-way acceptors. The expressiveness does not increase. But this was observed actually in a very old paper by Aho and Ullman in 1969, so that the two-way transducers are more expressive. So what's a two-way transducer? So I'm not going to define it formally, but I'm given a string, and at every step, I read a letter and I output something, and the two-way transducer can go back and forth, and it's deterministic machine. So this can do reverse. It's very easy to implement it. You go all the way to the end of the string, and then you come back. And as you come back, as the machine comes back at every step, you output what you read, and so what you output is the reverse of the original string. You want to swap, let's say you want to swap first name and last name, well, you need some regular expression to figure out where the first name starts, but you can go forward, find the first name, then as you read the first name, output it letter by letter, then come back, find the second last name, and output this last name letter by letter. So this model has been around for a long time, but it's not the most intuitive model. So for example, that's not how we reverse a list, right? And in general, the two-way machines don't really have structure. So the theoretical results have been very few and far with long gaps. So the model was introduced in '69, and then in '77, this is a very complicated proof which shows that the class of functions defined by these machines is closed under functional composition. Like if F is computable by two-way transducer and G is computable by two-way transducer, then G of F of W is also computable. Yeah.
Computable means on.
Right, yeah. And it can be implemented by a two-way transducer. Checking functional equivalence. So for one-way transducers, functional equivalence is this deterministic model. It's obviously decidable. For automata, it's decidable. It's very easy proof. For this, it turns out to be pretty challenging, and in '80, it was proved it's decidable. Then there is this kind of obscure work on MSO-definable graph transformations, and I'm not going to get into that, but there is some. So for regular languages, there is this nice logic-based characterization. So people try to generalize it and define MSO-definable graph transformations. This is a very nice result by Engelfried, which shows that these MSO-definable graph transformations defined in logic, it turns out if you restrict the graphs to strings, then the class of transformations that definable, it turns out to be equivalent to these two-way transducers. So it looks like this is a robust class. But the results are quite complex, and there are no known practical applications. So that was the place where we started investigating this, and I'm going to basically get into details of two things. So one is a one-way model which captures these transformations, and we call these streaming string transducers. So I'll show you through examples how we can compute these various transformations with exactly the same expressiveness. So this class, that's going to be the regular string transformations. And then I'll tell you about some recent work where we have a regular expression like declarative syntax for these functions and an implementation of a domain-specific language for this, which we call DREX. And this idea of regular functions actually generalizes to many other settings. And if I have time, I'll tell you a bit about that later, right? Okay, so here is a very simple transformation. Delete, suppose I want to delete all A symbols from strings. So the traditional transducer, this is how it would look like. It's only one state. If it reads a B, it outputs B. If it reads an A, it outputs epsilon. So as it reads the string from left to right, it's going to output the original string with all A's removed. So I'm going to model it a bit differently. So I'm going to have a machine with finite state control, but an explicit string variable, just like a program. So I have now variables, and these variables arrange over strings. And so this string variable is called x here. It's initialized to the empty string. And when I read an A, the x stays unchanged. When I read B, x gets set to x concatenated with B. So it implements exactly the same transformation. So why is this interesting? If I now start thinking about string variables, and my operations involve concatenation of symbols and string variables, I can easily implement reverse. So my reverse is y is set to the empty string. Every time I read a letter, it's added to the left of the variable y, right? So if I read an A, y gets set to AY. At the end, the value of y will be the reverse of what I read, right? So this feels like an infinite state machine. So you may want to think about it as infinite state machine. But basically, the control is finite state, and it has these variables which can grow unboundedly. And there are no tests allowed. If I allow tests on these variables, then the model becomes Turing complete. So in fact, this whole idea of regular functions, now it turns out that it's really the functions defined by programs with write-only variables. And now in theoretical computer science, people have studied programs with read-once variables and so on. But this kind of, offhand, it sounds a bit uninteresting. Why would you want write-only variables? But I'll show you various examples where they, in fact, implement very interesting transformations, and in particular, these regular functions. So suppose I want to implement the following thing, right? If the input ends with B, output reverse of the input. Otherwise, output the input with A is deleted, right? So this is, so the property depends on the global, which function I want to compute depends on the global property of the string, right? So if I'm going left to right, if you were to forget about this specific model, if you were asked to write a program to implement that thing, you would and you said, the requirement was do only one pass. In fact, the best algorithm would be doing it only one pass. You would have to compute two alternative outputs because you don't know whether the input is going to end with B or not, right? And the natural thing to do would be to have one string variable that computes one output and another string variable that computes another output. When we are done reading the string, you know whether the input ends with B or not, and you would output the right thing. So that's exactly what's happening here. So I have X is computing the string with A is deleted. Y contains the string reversed, the string that you have read so far reversed, just combining the two machines I showed you earlier. The finite state control is trying to keep track of whether the last symbol was B or not, like in the DFA. And if we end up in the right state, that's where the last symbol read was B, so we output Y. If the machine ends up in the left state, the last symbol read was not B, and it outputs X. And you can prove formally that these machines are closed under regular look-ahead. What that means is instead of having a transition depend on the current symbol, if it depends on some regular property of what you have not read so far, right? So that's a regular look-ahead. So you get a machine, and you can actually get rid of, you can compile that regular look-ahead away, right? Which is a property for DFS. And it's not a property for the classical one-way transducers because they won't be able to implement this transformation because you don't know whether the input ends with B or not. So this shows that having multiple variables is useful, right? So I have two, again, I'm not doing any test on X and Y. So I'm computing different plausible outputs, and I'm not interested in examining those. I have my finite state control is telling me which one I'm going to use. But I need both. Now here is a swap. So let's suppose my input looks like U1 followed by some special symbol, say colon, and then V1 is another string, sharp is another separator, then U2, and so on. And what I want to do is swap V1 and U1. Right? So this is really similar to swapping first name and last name. And again, now here I need two variables. So X and Y So basically, the variable y accumulates u, the string u that I'm reading. And so when I see, and the variable x accumulates the v part of the string, the string after the colon. So after the colon, we are in the right state where the x is accumulating the second part of the string. And when we see sharp, we tag on y, which has stored the u part, and we tag on y to the end of x. Right? So that's the basic idea. Right? So the so y stores the u part, x stores the v part. When we see sharp, we do a concatenation. So since these are, again, I don't need any test over x and y, but I need the ability to concatenate x and y. And a critical restriction that I need to stay within this class of regular function is that when I concatenate x and y, I set y to the empty string or to some constant. So the intuition here is that I shouldn't be able to do x assigned xx, because then I would be doubling in one step, and then I could do x assigned xx. So my outputs could grow exponentially. And that just sounds bad, and in fact, it takes you out of this class, right? So this is called single-use restriction or copyless restriction, which says that if you have computed some chunk of output, it can be combined with something else, but it should be used only once. You should not be creating copies of it. So this is the formal definition of the model. You have finite set of states. You have an input alphabet, output alphabet. You have some initial state. You have finite set of string variables. And then there is a standard state transition function. If I'm in some state, I read some input symbol, I go to some state. But the key extension is this variable update, which says that if I'm in state Q and I read a letter A, I set the variable X to something. So something appears on the right-hand side. So what's on the right-hand side? Well, it's a string over output symbols and the variables I have, right? So for example, I could say X assigned XY. And this copyless restriction means that each variable appears at most once on the right-hand side. And then a configuration, so it is actually a bit infinite state. So I have a state Q and then a valuation for all my string variables. So the program semantics is kind of obvious. It's like a standard program. And then it defines a partial function from sigma star to gamma star. So just like final state. So if I end up in a non-final state, that means on this particular input string, the output is undefined. So that's the model we call streaming string transducers. So these are a few properties of it. So it scans the input in single pass left to right. At every step, it's doing constant amount of work, and you can the variables may get appended with some additional symbols, but each variable can contribute to the final output only once. So because of that copyless property, you can show that the output grows only linearly with the input. And so it's computable in linear time. But recently, actually, Eric Alander has shown that these can be evaluated even more efficiently. So in fact, they can be evaluated in NC1, which is a parallel complexity class. We can get maybe some intuition by something that it cannot implement. So this would be merge. So suppose I give you two strings which are separated by sharp, right? And what I want to output is the first letter of first part and the first letter of second part, second letter of first part, second letter of second part. It's like merge or shuffle. And that would require 2 pointers. If you are implementing this as a program in a pointer-based language, you would need 2 pointers which you move synchronously. This it cannot do. So it can swap the V block with U block, but it cannot merge it like this. Yeah.
Can you check if it's
No. I mean, it's going from left to right. So it starts at the first symbol. When the string ends, it ends. But it's not material. I mean, I think it wouldn't really have to expressive part. It can do something like duplicate a string some number of times. So you can rewrite W to WW, right? So that's possible. And in fact, W to W to the power K for a constant K. So why are we interested in this? Well, one of the things that I started with was the class should be analyzable. We don't want a model for which is Turing complete, then we would already have said, right? So, but here things are actually very nice. Just constructions are more complex, but solvable. So the pre-post condition, a typical thing that we do in type checking, right? So if I give you L is some constraint on the input strings, L prime is some post condition on output strings, and I want to check, is it the case that every input in L gets mapped to an output in L prime? So that's solvable in polynomial time. Another question is functional equivalence. So as I told you that for two-way transducers, it was known to be decidable, but the lower, it's non-elementary decision procedure. Here we can show that it's actually, there's a nice algorithm, and it's solvable in p-space, actually polynomial in number of states, but exponential in this number of string variables that we have. And in fact, we don't have a lower bound, so there may be a better algorithm. But of course, the nice thing about the model is that its expressiveness coincides with these two-way transducers, which we already know is equivalent to these MSO definable string transformations. So we have additional evidence that this class, so now it has this additional characterization, and now for this one-way model, now we have these effective constructions. Okay, and so these proofs start getting a bit complicated, and since I have, I don't have much time, so I'm just going to tell you the results. But if you're interested, we can talk later. So I think I'm going to skip through this part, which is we have a particular class of programs that manipulate lists, and this program on the left really belongs to that fragment. And we can, so if you can restrict the way pointers are used in a particular way so that they correspond to what these programs can do corresponds exactly to the this regular functions. And for these, all these questions are decidable. Yeah. Right. So in fact, yeah, since you asked this question, let me just show you. So x dot next equal to y, that's allowed. X assigned some new cell, that's allowed. Current is a special pointer, and you can do current assigned current dot next. But x assigned y dot next is disallowed, because that would let you move pointers in sync, and that would take you out of this class. And so that's sort of the restriction. At first, it feels a bit odd. I mean, it's like cells have next field, but I cannot traverse. That's what it means. But what it really says is that only you should traverse the next pointer only for the current. And for the things that are lagging behind, you can keep some pointers pointing to these cells, and you can rearrange them. You can change their next pointers, and you can then do reverse and swap and things like that by changing next pointers. But you shouldn't be retraversing the next pointers on the part that you have read so far. Yeah. Right, or just the Turing machine. If I have a two-head machine, then yeah, things are undecidable. Okay, so let me tell you about this other so this, I don't know if this would be useful in practice. It's some peculiar decidability result. But I think the next part, I think is actually, we are very excited about it, and we are building a prototype implementation. So everyone knows about regular expressions, and actually every, Perl, to pick your favorite language, and it will support a library for this. And just to remind you, in regular expressions, the basic operations are, well, the empty string, the letter A, union, concatenation, clean star, these are basic operations. And of course, actual language may support lots of other operations, like intersection, which can add to the complexity, but don't change expressiveness, right? So the fundamental question here is that, what are the basic ways of combining functions? Now, something like SED would let you combine them in many ways, but there is no good theoretical understanding of that. And now we have actually a very nice theory. So this is a calculus of partial functions from strings to strings. And the way I'm going to define functions, the following property will hold invariant, which is that the domain of the function, the set of strings where the function is defined, it's regular. Right? So it can be characterized by a regular language. So what's our base function? Well, that's kind of obvious. For if A is my input, A slash gamma means if the letter A gets mapped to gamma, everything else is undefined. So it's defined only for the input A, and on that it equals gamma. A similar thing for the empty string. What's the analog of union? So if you think about the union, R1 union R2, we say that if matches either R1 or R2. What happens if it matches both? Well, in regular languages, it doesn't matter. But now if I'm combining functions and if I want to preserve the property that the answer is function, I can't say apply I can't allow for the possibility that use F and G because their results may be different, right? So it's really conditional choice now. We call it F else G. And it says that given an input, if F is defined, output F, otherwise output G. Right? So that's the sort of an unambiguous version of, or some asymmetric version of choice. Yeah. No, because if I just said F or G, right? And what if both F and G are defined? What would you output? I mean, you can define it in other ways. You could say it's undefined if both of them are defined. But you need a way of selecting, right? So that's the thing. Okay, but now let's get to more interesting operators. So what is the analog of concatenation, right? So here is the definition. So if I give you two functions f and g and an input w, what this definition says is if I can uniquely split the input in two parts such that f is defined on the first part and g is defined on the other part, then apply f to the first part, apply g to the second part, and concatenate the results. Well, I mean, at the high level, take a string, split it in two parts, apply f here, apply g here, and concatenate the result. The additional constraint is that the split should be unique, because if it could be split in multiple ways, then splitting one way will give you a different result from splitting some other way, and then which one is valid one, right? Yeah, because we want one answer, right? We are trying to define a function. So of course, in regular expressions, people have defined something called unambiguous concatenation, or if you are thinking about parsing, basically what we want is there should be a unique parse tree. That's sort of the intuition. Now the iterate, there is an analogous construct called iterate, which says that break the string up into multiple parts, apply f to each part, and concatenate the results. Again, we want the split to be unique. Now things start getting a bit interesting. So we need, since concatenation is not commutative, I also need left split. So this didn't show up in case of regular expressions. So what is left split? Is very much like split. So split the string in two parts, apply f to first part, apply g to the second part, but concatenate results in the opposite order. And that's really essential for swap. And as you can imagine, there is something called left iterate. Now this is too abstract, so let me just give you a few examples. So ID1 is the function which takes a letter and maps it to itself. So it says that if A, then output A, otherwise if it's B, output B. And let me define, delete A1, which is similar, but it says that if it's A, output epsilon, otherwise apply ID1. So it just says, it's defined only when the input is a single letter, and if it's A, it drops it. Otherwise, it outputs that letter. So iterate of ID1 gives us the identity function, because any string can be split uniquely into single letter chunks. And if I apply ID1 to each chunk and concatenate the results, I get the identity. But if I apply, if I iterate delete A1, well, I get the function that I had defined earlier, delete all A symbols. If I left iterate ID1, I get reverse, because it says that take the string, split it into single letter chunks, apply ID1, which doesn't change the letter, and concatenate the results in the opposite order. So now this is getting more interesting. Suppose I want to define if W ends with B, then delete is, else reverse. So this is this function. So this else reverse is pretty much, it's clear. So this, the left function, I want this to be defined only when the string ends with B. And so this is split, so this, B, the prefix of the string is fed to this delete A. And the only way to match this expression is if the last letter is B. Right? So the definition of split was given two functions f and g, is there a unique way to match this, split the string into two parts such that f is defined on the first part and the g is defined on the second part. Here g is this single letter function b. So the only way to match this split del a b over b is by if the string ends with a b. So that's, and finally, if I want to switch u and v, then it's a similar trick. I need left split because I want to swap v and u. I want my first function should be defined for strings that end with sharp. So it requires a little bit of thinking, but it's a compact expression. And once you get feel for this, you know, these are very much like regular expression-like things. The matching has to be unambiguous. That's the main requirement. So we started thinking, can we prove that this set of operators is complete for these regular functions? Right? Can we construct every regular function using these operators? And there were lots of challenges along the way. We need this a combinator called combine FG. It doesn't show up in regular expressions. And what this says is that return apply F and follow it by applying G. So it's like multiple passes. And if I want to map an input string W to WW, I need this. I cannot express it without combine. But if I have combine, it's very easy to express. It's combine ID, ID. You know, apply ID, follow it by another application of ID. Right? So this is reminiscent of intersection of languages. Right? So so if I have R intersect with R prime, means first check does it match R, and then check if it matches R prime. And in this case, actually, we are concatenating the results. So things are, I mean, there are some analogies, but there are some differences also. And I have one final operator. And so this is actually took us a while to find this operator. So let's go back to this task that I have some bunch of entries, and I want to move title from every entry to the previous entry. Right? It turns out this is a regular transformation, and I could have written an SST to compute this. But in terms of these functional combinators, can I do it? So we don't have a proof of this, that with these other operators it's not expressible. But I have a strong intuition or conjecture that it cannot be expressed using the operators that I showed you so far. Because all those operators, what they're doing is they're splitting the file into chunks, applying transformations to those chunks, and combining the results. And we are allowing different orders, maybe reversing or, you know, the right concatenation versus left concatenation. But here, what I really want to do is to the content of the ith output entry is constructed out of contents of ith and I+1th input entries. And if I were to, so we tried various things like splitting them in some other ways, but it didn't quite work. But we have this operator called chain. And so it takes two arguments, a function, and the second one could be a function or just a language. And so given an input, what we do is split the input into multiple chunks. And these are the chunks that match R. So this is really like the iterate function. And again, the matching has to be unique, like in unambiguous parsing. But now what we do is apply F to the first two blocks to get the first block of the output. apply f to the second and third block to get the second block of the output, and so on. And my result is going to be this v1, v2, v3, v4. It seems like this was derived from that particular example that I showed you. And now the question is, with these SSTs which have these multiple variables, is it, does it capture all of this? And I'm really proud of this theorem. So it took us actually many, many months to prove this, which shows that the function is regular. So it's computable by these SSTs or two-way deterministic transducers, if and only if it can be constructed using these operators, like the base functions, the choice, which was the analog of union, then split and left split. So you need both versions, which were the analogs of concatenation, combine, and then this chained version of iteration. Well, if I have the chained iteration, I don't need the basic iteration because it's just a special case. That's a good question. We don't have proof. So actually, the structure of these is not understood. These are very new results, and we don't have learning algorithm also. I mean, so there is no analog of, say, theory of congruences or something like that. Yeah, or like pumping lemma. So how do we prove that something is not regular? Well, there are no tools. But we said, let's try to build actually a prototype language. So this Drex is that language. And so the first thing we did was, well, dealing with individual symbols like ABC is like too painful. So in general, we can have these sorts. And there's a very nice idea by Vianus called symbolic automata, where instead of having single letters, you can have like a sort, and you can have predicates over those sorts. So we use that to build our language. So for example, you could have a list of items, you could have list of numbers, you could have a list of Unicode characters. So the basic theory doesn't really change. But the next challenge was the obvious way to evaluate this was the dynamic programming algorithm. And the first implementation we had was of that, but it's cubic, and that's too slow. So we are not, I mean, of course, there are these results that equivalence is decidable and so on, but we are not, in terms of implementation, we are not even there. We are just interested in evaluation. Given the program and the input, compute the output. And one of the motivations was in SED and Perl, you can write some things where just evaluating it takes forever because it requires nested loops, or maybe it's too complicated, right? Yeah. So we developed a type system. So because given the connection to the PL world, we said, well, what if these combinators are used in some special way? And so in particular, let's say FLG. What if this is used only when their domains were disjoint? And in many examples, they are, right? So this, of course, requires the programmer to restrict attention to like a very specific discipline of expressing things. But we can show that it doesn't really lose expressiveness. Similarly, in split FG, what we require is a very strong notion of unambiguity. We say that for every string, there should be at most one way of splitting in two parts such that it matches F and G, right? So not just on the specific string. So again, this doesn't lose expressiveness, but requires you to think, right? Yeah. How to express some particular transformation. But then this gives us actually a nice foundation. So we have a implementation with this type system to enforce consistency rules. There is a theorem which shows that insisting on this consistency does not limit the expressiveness. We can still express all regular functions and only the regular functions. Checking consistency itself, I mean, so the system does type inference, so you don't really need any type annotations. So given a program, whether it's consistent according to these conditions, that's checkable in polynomial time. But the most relevant thing is that no matter which program you write in this, if it's strongly typed, then it can be evaluated in linear time. So this is the the kind of result that we would like in from a good type system, right? So and we have an implementation, and in fact, we can write transformations in this language, which the natural way of expressing this instead would require would require a nested loop, and the system won't be able to get rid of that nested loop, and hence our implementation would be much faster, even though it's just the first prototype. So, and this evaluation algorithm is actually quite interesting, and I'm running out of time, so I won't get into that. Yeah. So we have some evaluation. There is actually a paper in the upcoming POPL on this implementation of this language in the type system. So how much time do I have? Okay. Okay. So I'm not going to. I have to skip all these things, but this basic thing that maybe I should go to. Yeah. So this is my second last slide. So I told you about finite strings to finite strings, where there is actually, I think, a good practical motivation. But from a theoretical viewpoint, you can ask, okay, is this idea restricted to strings to strings? Actually, strings to strings is really strings to a monoid. So the monoid here would be the set of strings, output strings with concatenation and empty string as the identity. Right? What if it's a set of natural numbers and the binary operation was addition? So that's really finite strings to a commutative monoid, and we get, again, a very nice class, very robust structure. The theory is much simpler because the output set is commutative. We have work which extends this from infinite strings to infinite strings, and variety of other things. There is a lot of work in the literature on this weighted automata and mapping to semi-rings. We have now a new class with very different and interesting properties, lots of open problems, lots of unexplored classes. But in general, all these definitions involve a finite state machine with a set of write-only registers, and the combinators and the definition of regularity is parameterized by the combinators that are used to combine the registers, right there. So that we call that model cost register automata. So where the registers hold values from some arbitrary domain, and the operations are some a specified set of operators. Okay, so I will stop here. Thank you.
Let's thank Rajeev.
Any questions? Yeah, go ahead.
If you allow defining recursive functions using your combinators and recursion, do your consistency rules keep you in the same class, or do you get more expressiveness?
Oh, that's no. The consistency rules are defined only for our combinators. Yeah.
Yeah, but could you think if that?
So I wouldn't know. Yeah. But I think if you throw in recursion, I'm sure everything becomes Turing complete. Yeah.
But I mean, it would be along the same lines. So it's very nice that you have this result, a bunch of these specific operations. But of course, from the language side, you'd like to not see so many specific operations, but just maybe a couple, and then some combining form, which will preserve the overall property. It won't be recursion, but maybe it's a restricted form of recursion. It's kind of a regular recursion, where the sequence of calls has to match some regular pattern or something of this kind. So have you done something along the line of general combinations rather than these specific ones?
No, that's a good suggestion, but yeah. I don't know. So I think the structure is, this is very new work, and the structure is not well understood. So the hope here is, actually, if you think about regular languages, right? So in the end, what we are interested in is that does the string satisfy, is it in this language or not, right? So you want a binary decision. But to make that decision, you need these auxiliary states. And in fact, the basic definition of regularity is the number of auxiliary states that you need to compute your final answer that's finite, and that's unique, that's canonical, and that's used in almost for every result in automata theory builds on that intuition, right? Showing irregularity, learning, minimization. Now here, so if the string ends with B, delete A's, else reverse. So that's the function I want to compute. I still need to compute delete A's and reverse. So the complexity of this is two. I need these two auxiliary functions, and my variables are really computing these two, right? So one would think that maybe there is a set, there is some class of, there is a class of supporting functions that are being combined in some regular ways, and the structure is very canonical, right? But that such a theory would be necessary to answer your previous question, and also, to do minimization, learning, and things like that. But we are not there yet.
Okay. So you mentioned Solani, right? Could his functions in his DSL be expressed as regular functions, or so you mentioned the word by Solani, right? Solani, sorry.
Right.
In the beginning, on synthesizing his DSL for flash code. Can his functions be expressed as regular functions?
That's a very good question. So yes and no. So yes, for his earlier work, which was really the theoretical work, the academic prototype published in Popper, but no in terms of what actually goes in Flashfield, where there is lots of domain-specific information and all kinds of things built into it. For example, the synthesizer knows about formats for dates and how to convert dates and all kinds of real-world knowledge, and that's beyond. It's not a pure string-to-string transformation.
It seems to me that input sanitizers and output classifiers can be described as regular functions. So it's
Yes,
maybe
in fact,
a useful application where you prove certain things about. Have you looked into this?
yes, oh yes. So that's a very good point. So there is this tool called Beck where it builds on the traditional finite state transducers, and it's for string sanitizers. And they do implement this checker for equivalence. So for example, if I have a sanitization routine F1 and F2, but if I can prove that F1 composed with F2 is equivalent to F1, then I know that F2 is redundant. And so there is a build, there is a prototype implementation and a tool. And in fact, if in their paper they have an example, and the example is that I want to delete the string after the last % sign from the URL. And they say, well, the traditional transducer cannot do it, and that's why Beck doesn't support it. But that can be expressed very easily here. It requires you to find the last % sign, which is exactly so it's actually unambiguous, but as one-way finite state machine, classical machine going left to right wouldn't know when it encounters a % sign, is it the last one or not, right? So yeah, so that's this Drex with its analyzer build, that would be one of the
for specifying classifiers, so there you might have, say, so maybe not all the classifiers are good for my program, so I want to say that describe these are possible classifiers, and then I can specify one, the user specifies a particular, and then you can check if it's compatible. Has it been applied for privacy also, or only for
yeah, not yet. So the tool is just it's being built now. Yeah.
Okay, last question, Rajeev.
I have actually two related questions. The first is in the late 90s, Carlin and Schwartz looked at verifying programs operating in pointers, which is one of your motivating examples, using monadic technologic on strings. And they also looked at DSL systems and see. Have you looked at their work? Is there any relationship with some of the stuff you're doing?
I don't know exactly what the relationship is. Yeah, but for example, Bujani has done work on this regular model checking where you specify the state of the system as a string or as a tree, and then your single step is actually a regular transformer for strings, right? So that's not quite related, because what they're doing is they're expressing the transition relation by a transducer, and it's a classical transducer, but you don't get guarantees of fixed points. So whereas here you would, so that's probably applicable for a larger class of programs, but you don't have any decidable property for some global thing, right? Yeah. So I think so I suspect this is also in that style where you view the heap as a tree, and you view the single step of the program as a tree rewriter, right? So whereas here it's the whole transformation, which is really the fixed point of that rewriting, is expressible as a regular transformation. So it's, of course, it limits you to a smaller class, but then you have the bigger decidability guarantee, which is termination of the program. Yeah.
Also, if you consider extensions to languages on trees instead of string, seems like kind of a natural.
Yes, so we have, trees to trees. We have a paper called streaming tree transducers, which extends this to trees. And there are lots of potential directions. There are actually more open problems and directions and potential applications than we have bandwidth for.
Okay, thank you. And